section that this neuter current we discussed, their conservation is based on equation of motion. If you remember, I used actually the fact that Euler-Lagrange equation take place. Let me add that there are different type of conserved current, so-called topologically conserved current. It's just for your curiosity, if you still. Which are not based. I just show example. So take some anti-symmetric tensor, not necessarily QED, but just in order you would understand it. So F mu nu equal minus F mu mu. Introduce current. Say for example mu, which is d mu F mu nu. Then it's clear that d mu j mu equal 0 because d mu j mu equal j mu d mu F mu nu equals 0. Indeed, it's anti-symmetric, but this symmetric. That's it. So it's 0. And we do not use any equation of motion. So it's example. So it's used, but it's not connected with our course, just for your curiosity. Sorry? Say again.
Why do you say this is a topologically conserved?
Topologically, because usually this anti-symmetric combination connected with some topology. Okay. Yeah, it's just a name. Okay. Now let us discuss. I will erase this. It's just as I said. What I will start before considering already quantum, we should just discuss general solution of KG equation, first classical, because our analysis will be general. Klein-Gordon equation. Okay, so our equation, it's PDE. First of all, this is PDE, partial differential equation, linear, quite simple. And I will use this stuff, d mu plus m square by x, right, equal 0. Okay, there are different methods to get general solution, separation of variable and so on, but simplest is take the Fourier transform. take the Fourier transform of phi x 0 x. Then we have, oh, sorry, just fx. It would be better already to use this fx, right? Then we have, by using this, do I have Fourier transform here for only delta function? Right, but you have, right, Fourier transform definition. Oh, okay, Fourier, right, you have, right? Exactly. This is even, it has number, yeah, 2a, right? Equation. So we have this d4a 2 pi to the 4 and pi tilde k. Substitute it into KG equation, which is written here. What we will get? Something nice. Nice, because you should consider derivatives, and they it's easy to take them. You should just consider derivatives of this exponent. Then you will get this k mu is minus plus m squared, and it's equal 0. You see, this guy equals 0 at all x. Then usual stuff, it's possible only if this integrand, the whole integrand minus k mu plus m squared y tilde k equal 0. Now we have something similar what we had here. This is properties of, so if we have x times phi x equals 0, then the answer is that phi x is just delta x times some regular function. So from here, we have that answer is phi tilde k equal delta function. And I will now write explicitly k mu over k mu. Okay, so minus k mu, right. K0 square plus k square plus m square. And how I use, okay. And this is f tilde k. And this guy is arbitrary, regular. So it's satisfied because like x, delta x equals 0, I have this stuff. By the way, I should say we will not use, it's not important, this property. Delta function is symmetric function. Delta x equal delta minus x. You should, sometimes it's useful, but it doesn't matter in our case. Okay, now from here, let us substitute this stuff instead. This product, we substitute our answer, right? So it will go up. Okay. Right? So we came, just substitute, and we have so I want substitute in phi x, okay? Just substitute f tilde k. Substitute, and we have delta okay, it's our solution. So we got solution expressed in terms of arbitrary function f tilde k. But now we can do better. We can integrate over k0. And now let us use this property. Right? So this is, let's consider this guy as function of k0 and consider this property. Okay, now our function is actually this one. And let's find zeros, right? Of so this is actually our function k, right? This argument. So there are two zeros. One is this. And another this. Okay, now let's integrate over k0. I will use this formula, right? We should take derivative of that function over k0. Let me write answer. So I integrate integration over k0. This delta function kills this integral. So this will give me the following. Maybe it's better to write arrow and phi x now equal this. D3k over 2 pi 4. And now we should put in denominator, you see, df dk0, this function, is nothing else but minus 2k0, right? And we should put in denominator absolute value of this thing. And then we have two terms, like in that case. It's same for this and this root, because minus doesn't matter, right? So we absolute value, this is formula in that case. Okay, then what we have is this. Let me write. Okay. I will consider now, I will write in this form. And then we will talk. And here we should put k0 equal omega k, which is nothing else but this positive square root. Okay, point is that we have one exponent with minus, but we get minus when k0 is positive now, right? I will substitute for first 0, right? We will get minus. So this, right, kx now look like, it look like that, omega k x 0 minus. So you can see k0 disappeared. Oh, here is bad mistake. Omega k, of course, is expressed k square plus m square, right? Because we have those two roots. I miss nothing. So for positive, I have this exponent. And for negative, I get minus. And because of that, I have plus here. So it's OK. And now I got rid of k0 because my omega k is just function of k squared. And that's it. And this guy now could be substitute because k0 is omega k, right? I could just write this. Omega is positive by definition. So this is function of k, you can see. So everything is, it seems okay. And those two functions, they now depends only on k vector, because k0 is fixed. They are arbitrary. Okay, phi plus minus k are arbitrary. This is general solution. And in general solution, PDE, you always have arbitrary functions, right? Okay. Now we have still constraint, not completely there arbitrary, because this is real. Phi complex star x equal phi x. It's easy to check that this guy leads to the following stuff, that phi, maybe it's better to write minus plus in parentheses, minus k is equal phi plus, okay, let me write. I could actually now consider that z depends on this stuff. Just one moment. Yeah, it's okay. So this is okay. Right. Complex conjugate. Why? Because you see, if I take phi complex conjugate, I will get complex here and here. So this guy with minus should become phi plus because it's still same function, and phi plus should become phi minus, phi plus complex conjugate. So just check this. I only want to be sure that there is no minus. It seems it's okay. Right. Yeah, I believe it's okay. It's okay. Right. Okay, so we have this constraint. Now, in order to follow notation of Peshkin, it will be convenient to redefine those arbitrary functions. To redefine phi plus k s, let me write s, there is 2 pi, it's just convenience, nothing, no physics. You will see, I explain later why. Then it leads this guy, if I redefine, so it's convenient, S, this guy. Then phi x, oh, yeah, so it leads phi x. This is quite common notation used in field theory, those A, and yeah, you will see 2 pi q, 2 omega k. Of course, they still depends on time, but just k0 here is fixed. And this is complex conjugate. And as I said, you should substitute everywhere k0 omega k. Omega k is defined. Okay, this is final general solution, right? Okay, could be why? No, it's okay because I had omega k, then I substitute instead phi plus this guy, then I cancel part and I got in omega k, right? Oh, square root of 2, you mean? Right, because there is 2k, you correct, right, I agree. Square root of 2, right? This I agree. Thank you. Thank you. Oh, okay, I could write something like that. Thank you, yes, sure. Right. Okay, so this is general solution. In classical theory, so we have, this is solution expressed in terms of plane wave. And we have plane wave with arbitrary wave vector in classical field theory. Omega k is called frequency. K is called wave vector. That's it. So it's general solution, and we will use this general solution many times. At last, we come to quantization of Klein-Gordon field. Okay, I could write here quantization. Now review quantum mechanics. Yeah. Okay. So quantum mechanics. We have in quantum mechanics those classical, if we consider Hamiltonian formalism classical, so we have momenta and coordinate and I, some finite number, but it could be any number of degrees of freedom. So they become operators, right? We have in quantum mechanics, there are Schrödinger picture, Schrödinger and Heisenberg picture. In Schrödinger picture, those operators are time independent. Instead, wave function, of course, depends on time. We have commutation relation in this picture at all time because they are time independent. Qi Pj equal I H bar delta Ij, but our units H1, so this is just I delta Ij. And then we have 0 in the case of commutator between coordinates and between momenta. In the Heisenberg picture, we have independent of time wave function and depending on time those operators. So in Heisenberg picture, this relation are still valid. Now Q and P depends on time. Are still valid if Q and P are considered at the same time. So this is equal time commutator at the same time, but arbitrary time, but same. Now go to field theory. In field theory, we instead QI is replaced by field, right? So let's consider Schrödinger picture. So this operator QI replaced by field. X plays the role of I. It's index. It's not operator. It's just index. Now we have continuum number of degrees of freedom. That's it. And of I. And what we found, momentum density pi, we found in Hamiltonian formalism, pi x play the role of pi. Then fundamental relation, commutation relation. Okay, instead, relation between Q and P, we have commutator between phi and pi. Sorry, Y. So this is IJ. Did I write correctly? Yeah, you see? So I should use now here. Right. Actually, this answer. So X and Y play the role IJ. Now we have still I, and instead Kronecker function, we have delta function. So you can see explicitly it's shown that it's indeed X and Y plays the role of I and J. Remember that dimension of phi and pi different than Q and pi. We will come to actually dimension. I will find including. So you want to, and other commutator looks like that. Phi X, phi Y equals 0. This is, oh, I made mistake. I should, of course, use this, but sorry, it's already played. In order you put, yeah, it's my mistake, sorry. Anyway, we have those three relations. This, I substitute I is retained, and instead Kronecker delta, I got delta X minus Y. And those 2, 0. One this and another this. Phi. This is Schrödinger picture. And I would like, in Heisenberg picture, what happened, also write, please. It's same, essentially. Now we have, of course, time. And we just write same time. We can write those relations as model independent only time, same for phi and pi, like in quantum mechanics for Q and P. Same relation. And this is same. When we take time the same, it's wrong in the case of different time for, say, phi and pi here, or for 1 5 and another 5. We will find in this theory exactly those relations where, when those time are different. They are quite complicated. Essentially, they express through Bessel and Bessel function. Okay, so this is concerning Bosch, Schrödinger, and Heisenberg stuff. Now, we have classical general solution. We can use it now in quantum theory, but we should reinterpret this quantity. Those were arbitrary function of 3 k vector and so on. Now they are operators because this is operator. This guy is operator. So everything here is numbers. Of course, those k, x, those a star are operator. Okay, now go to the quantum field theory. So as I said, phi x, pi x operator. The reality condition is different now. Not complex conjugate, but phi equal phi dagger. So this is Hermitian conjugation. Hermitian conjugation. Like in linear algebra. Remember that if your matrix is Hermitian, satisfy this condition, all eigenvalues of that matrix are real. So it's really reality condition. So this is Hermitian conjugation. Therefore, let me general solution rewrite in quantum field theory is. This is, of course, Gordon only we consider.
It's just scalar.
It's true. It's scalar concerning Lorentz representation. But now phi is operator. It's not, function really, it's operators. We just assume this. So what we would like, a kind of quantize this classical theory. In this classical theory, we have classical field. But now it's operator value. So at each x, you have its own operator. It's like before in quantum mechanics, you had a coordinate operator. In classical mechanics, you have just number, q, right? In quantum, this is operator, actually infinite matrix, if you want, right? And at each I, you have different. I index takes 1 to n. Here, you have different operator, infinite matrix, if you want, at each x vector. Because vector coordinates, this is a kind of index. So you have now continuum number of matrices, if you want. But of course, we will be smarter, and we will use different language. Like in quantum mechanics, historically, quantum mechanics started from, who remembers, from Schrödinger equation or from something else? From matrices, actually. The first paper by Heisenberg, this is paper with matrices. You see, no Schrödinger equation. He did not know this. This is why he used Heisenberg picture. Schrödinger was later. Essentially independently. It's interesting story itself. You see, so this is the point. So now phi is scalar, you are right, but scalar operator with respect to operator field, operator valued field. Right.
But X is not operator then.
Yeah, I emphasize that coordinate X plays the role of index ij. Yeah, many times I said this. This is important. So you just, instead I, you have X. You have continuum parameter. It's just parameter. Not always. There are some theories, for example, in string theory, X is also operator. There are also non-commutative theory, field theory, not string necessarily. Again, it's operator. But in conventional quantum field theory, it's just index, but continuum index. It's like in classical mechanics and classical field theory, right? Index I becomes X. You could, of course, consider to discretize string, for example. Then you will get indexes instead X, for example, right? Okay. So the general solution we can rewrite in this form is phi X. This is a solution in Heisenberg picture. I will write this because it depends on T here. I will write this, emphasize. Okay, okay. It's better to write even T. Let me write explicitly, maximally, because it's very important. D3P, not K, I will use just to emphasize the difference. I will discuss it. Not omega K, I will use index E, P. And here I have, okay, those K. Okay, I will use a little bit different now notation, sorry, like Pashkin use. Now here, not complex conjugate, so I will put, and even to be explicit, I wrote P. Not complex conjugate, but Hermitian conjugation. This is still Minkowski product, including P0. And now the last, P0 equal E P, which is equal square root P square plus M square. Okay, now let's compare classical theory. We had K. Of course, you could use also K in quantum, but in order to compare, I use different notation for momenta, essentially. But in classical real theory, this is not momentum. This is frequency, of course, not energy. And this is wave vector, as I said. So those guys goes to they go to P0, which is equal and this is energy. And P momentum. Of course, if we consider H, we would use this notation, P0 equal H bar, Planck constant, K0, and P, this is H bar, K. But in our case, H1. And as I said, instead A star, we have a dagger. So now actually those operators connected, and we will see this not just with wave, one can consider as wave, but also with particles, because this dispersion relation, if we interpret like energy momentum, this is Einstein relation for particle. Classical particle he considered with mass m, when c equal 1 and we do not have h equal 1. Okay, let us start to do the dirty part, quantization in Schrödinger picture, just explicit quantization. This is just very useful. So let me say again, this is written in Heisenberg picture because this is operator, analog of coordinate, it depends on t. T is here. This is Minkowski P0T here, right? But Schrödinger is simple. To get Schrödinger, put t equals 0. That's it. This will be Schrödinger picture for operator. Okay, so we have this. Now I should be careful. Still have some time. I will just introduce. Maybe some questions. Yeah, please.
In the Schrödinger, what carries time dependence in the Schrödinger picture?
Wave, right. In Schrödinger picture, you have wave function, which depends on time. In Heisenberg, all wave functions are time independent. Okay. So you have Schrödinger equation, which show how wave function depends on time, right?
Yeah.
But in Heisenberg picture, your wave function is time independent. You could take in Heisenberg picture wave function like, for example, Schrödinger, from Schrödinger picture at t equals 0, something like that. So this is different. There is simple, it's you in quantum mechanics, look at any text in quantum mechanics. We will come to that at some point, soon actually. there is simple unitary transformation between those two pictures. We will come to that. I don't want to talk right now. They're equivalent physically. It's just two different descriptions of the same physics. Okay? We will see this.
So is the Schrodinger picture a valid picture for all field theories? Is this
In principle, yes, but
because, for example, wave functions cannot be defined always.
no, you know,
For a
it's
field theory.
okay. Point is that problem in field theory, as you know, wave function depends on coordinate in the case of Schrodinger picture. And when we have field theory, this is not coordinate, but classical field sum. You have variational. We should not talk about that. You know, it exists. It's very inconvenient. Okay, let me put it this way. It exists actually. I could write a kind of Schrodinger equation, by the way. We never will use in this course, but it will be variational. You see, but in principle it exists, quantum field theory, but nobody succeeded in using it. It's true. But at some level, like free theory, one can get, because we will get exact answer. This is simple theory, so it's okay. Okay. Okay, so I should. Okay, sorry. This is the last. Okay, so as I said, we have. Oh, it's better to use it. This order is better. So we will consider right. Okay, so we have this, as I said, now key-independent fields. And key-independent momentum density. And this we already know that this guy is nothing else but momentum density derivative with respect to time. And now we should take this derivative at t equals 0. So we have this commutation relation I wrote, right, already. I will not repeat them. This. So we will use this commutation relations, right? And let me call this one. So all this line, I will use this one. Right. We have the general solution where it is here, right? It's not right. I will use still this stuff. It will be 2 for today. So it's Heisenberg that I will use because I could, for example, to get by using Heisenberg derivative with respect to t at t equals 0, then I get pi and so on. Right. Okay, so this is this. So phi x, right, at t equals 0 is in equation 2 just at t equals 0, right? So just put here t equals 0. And let us calculate pi x. And I will write answer. It's easy to check. Pi x, taking this derivative, this stuff, is it. Yeah, actually, right. No, maybe I should write before. Right. Still, maybe 5 minutes. We at least start next time from there. So I will write. Okay, then pi x are in equation 1. Phi x, just take t equal 0, and we have d3 p 2 pi cube. You will understand why I now p. Just let us write everything. And I will rewrite in this form. I could do this. D3P. And I will write those two lines and I stop today. Phi D and this exponent. Now pi x, it's easy, right? Just take derivative with respect to t. It's written here and put t equals 0. So let me write will be simple answer. D3P over 2 pi cube minus I imaginary units E over 2 A P dagger and this I will rewrite as this. It will be convenient for notation. So I will start from that next Wednesday. Or maybe I should write how this phi and pi express through, yeah, and then I start through A and A dagger. Okay, not actually here. It's okay. I will come to that. Okay, so let's stop here, and I could still answer your question if you have. I, by the way, forgot to answer your question concerning whether we can use for gravity this 1-1, right? You ask. 1-1, but we used it. Point is that what I said, G mu nu actually is reducible representation. It composed of two. This actually exactly this what you want, but also 0, 0. Point is that G mu nu, you could write two types of G mu nu. Traceless okay, let me write G mu nu. Okay, I will write in this form. It's a little bit easier. So this will be this minus 1/4 G mu mu. This is trace. And you have G mu mu. It's non-zero. You see it's 4. So this guy corresponds to 1-1 because this representation anti-symmetric but traceless. It contains, you remember, number of degrees of freedom we calculate m plus 1 times n plus 1. M in our case is 2 because this is, then we have 3 times 3, 9. It's exactly traceless.
Yeah.
But it's not enough because we still have trace, which in gravity is used. It's non-zero. Even in flat space, it's non-zero. So we have actually 10 degrees of freedom in gravity field. But this is used, what you said. Of course, we have. Mm-hmm. So everybody is free. Thank you. And see you next Wednesday.